Welcome to the Queens College Physics Department's third lab in the summer series for 122. This is our Resistivity lab. The details will be explained in the accompanying Google Doc. I'm just going to give you a look at the equipment, how it's used, how I collected the data that you're going to be working on, and I have a couple of interesting things to show you as well. This is my power supply. I'll be using it as a constant current power supply. That's different than you would normally get with the battery. The battery is constant voltage. Here I'll be adjusting this so that the current is always the same and the voltage will just jump around to suit the situation. The power lead comes from here and goes to a current meter, which is wirelessly connected to the capstone file. And from there, it goes back through this system here. This is a wire. I have a whole series of wires, different materials, different thicknesses. I have one in the thing right now, in the frame right now. It's connected here and here, and these make the connection, and I can adjust this one to change the length. These two leads read the voltage here. So the way I collected it is I have capstone running. I turn on my power supply. I tell the capstone to go, and I simply adjust the current. As I increase the current, the voltage goes up naturally enough. And while it's absolutely unnecessary, I did take the time to adjust it so that the data looks nice. I don't have time for this. None of us have time for this. Anyway, I did. There you go, there. This wire for 24 centimeters with a current of 1 amp running through it. Stop that. Current of 1 amp running through it has 0.035 volts. That's the voltage across it. And that's how I did everything. I did 4 different brass wires of different diameters, and we're going to plot the cross-sectional area against the voltage. And you're going to compare different materials, and you're going to compare different lengths. And that's it, except for I have a couple of interesting things I want to show you, and that's coming up next. There's one last thing I'd like to demonstrate. We haven't talked about the effects of heat on a material and its resistance. Normally at this point I'd be going for an incandescent bulb, but we're going to settle for halogen because it's all I could find. I switched to LEDs long ago. I have a halogen bulb connected to the signal generator on my capstone interface, and I have the hardware set up like this. All I have is a sensor on the output, and I have the signal generator here. I have it set up with a triangle wave. I'm actually going to increase this to 1 hertz. Won't need it to be crazy, but it was a little slow. Actually, you know what? Let's be at 0.1. Maybe slow is better. 12 volts, 12 volt bulb, and it's ready to go. So I record, and I have a little dot right in the center, and then I turn on. And at first it goes through a heating cycle, and now it's alternating in current, going from 0 to a current that'll give us 12 volts, back and forth. You can see it pulsing, in the inset picture. Slowly. Now ignore the first little loop, but then you get that really interesting shape, which is clearly not following Ohm's law. I'm plotting here voltage over current, so it should be resistance. But because the filament works by heating itself and glowing incandescently, temperature becomes a factor. What you're seeing here is something called hysteresis. Hysteresis is when the material has a memory for where it was before. So if I turn the bulb on, I drive current through it and force it to heat it up. I drive it. But when I ramp down, I'm not driving it down. I'm letting it cool naturally, just with ambient conditions. So those happen at two different rates, and that's why you see two different curves here. One is for the cool, and one is for the heating. Anyway, just a quick demonstration of why we don't use light bulbs in circuits that are meant to be resistors. I changed my mind. There's one more thing I want to show you for a little bit of context. What you see there is, well, it's just a holder that we made up for resistors. You can see the resistor inside, little metal pieces coming out the side and bands of color, which you can't read because it's too small. However, this is a 68 ohm resistor. So I can do the same thing I did with the bulb. I can hit record, and I can do this, and I can turn on my, and there you go. It's doing the same thing. It's a triangle wave. This is going from negative to positive to negative to positive. But you can see that it's a lot better behaved. That should be enough. And if I take fit, I get 68.4. 68.4 is close to 68. It's not exactly 68 because this is a plus or minus 5% resistor. They leave a little bit of leeway in there in case people overheat it or abuse it in some way. And that's it. This time for sure. You're off the hook until Wednesday. Bye.